Simple linear regression is a statistical procedure that allows us to use one variable to make predictions about another variable. This video describes various aspects about regression, such as what is meant by a line of best fit, how to interpret the intercept and slope coefficients, the way we define residuals and how to compute the standard error of the estimate. You will also learn about the assumptions of simple linear regression and how to test them. Finally, you will learn about standardized regression and its connection to correlation. Let's start with an example. Here you see a scatter plot of Galton's height data. Mid-parent height is on the x-axis and child height is on the y-axis. Mid-parent height is the average of the parent's height. This plot suggests a moderate positive correlation between mid-parent height and child height. The correlation between these two variables is 0.5, which indicates that mid-parent height explains about 25% of the variability in child height. Correlation is a statistical procedure that tells us about the strength and direction of a linear relationship, but it does not allow us to make predictions. To make predictions, we need to fit a line to the scatter plot. Once we have a line, we can ignore the observed points and make some predictions. For example, if we start with the value of x, we can go up to the line, and then over to the y-axis to get a predictive value. There are many ways to draw a line through a scatter plot. We would like to use a best fitting line, a line that provides the best fit to the points in the plot. Let's look more closely about fitting a line to a scatter plot. Here is another scatter plot that uses simulated data for 10 observations. We can fit a line to this plot using the equation for a line, y equals a plus bx, where a is the y-intercept and b is the slope. Let's set the intercept to the mean of the y values and the slope to 0. That gives us a horizontal line drawn at the mean of the y values. This line is one of the many possible lines we could draw in this plot. However, we would like the best fitting line. In order to judge the quality of the fit, we compute a residual. A residual is the difference between an observed value of y and the predicted value of y. The dashed vertical line in this plot illustrates a residual value. It is clear that the distance between this point and the horizontal line is large, which means the predicted value of y is very different from the observed value of y. The fit of the line for this one point is not very good. However, when fitting a line, we are not interested in the residual for a single observation. Rather, we compute residuals for every observation and summarize them with the sum of squared residuals. This statistic is obtained by squaring the residual for every observation and adding the values together. Values close to 0 mean that the points in the scatter plot are close to the fitted regression line. As the value of the sum of squared residuals increases, the quality of the fit decreases. However, keep in mind that this statistic depends on the scaling of the outcome variable y. If we compute the sum of squared residuals for our horizontal line, we get 69.25. Visual inspection of the plot suggests that we can find a better fitting line. Let's try different values for the slope and intercept. We will arbitrarily pick a few values for now. This plot shows a line with an intercept of 34 and a slope of 0.5. It appears to fit the data better than the horizontal line we tried previously. The sum of squared residuals is 57.11, which is lower than the sum of squared residuals for the horizontal line. Although we improved the fit, let's change the slope and intercept to see if we can do better. With an intercept of 25 and a slope of 0.7, we clearly missed the mark. This line is a very poor fit to the data. The vertical dashed lines illustrate residual values, and they are all clearly very large. The sum of squared residuals is 317.8. This value is much larger than any we have obtained thus far. Let's change the slope and intercept again. This plot shows a line with an intercept of 19 and a slope of 0.7. The fit is better for this line than the one on the previous slide. The sum of squared residuals is 60.51, but we found a better fitting line earlier. We can continue with trial and error in this fashion until we find the best fitting line, but it is very inefficient. There are an infinite number of values we could use for the slope and intercept. We would have to try all of them to know which one is best fitting, a task that would take us the rest of our lifetime. Thankfully, there's a better way. With a little calculus, we can derive equations for the slope and intercept that minimize the sum of squared residuals. This work has been done for us, and all we need to do is use the resulting equations in our calculations. These equations for the slope and intercept will give us the best fitting line. By using them, we can fit a line to the scatter plot, and there will not be another line that has a smaller sum of squared residuals. The interpretation of the slope and intercept is straightforward. The slope is the amount of change in the outcome variable that occurs with 1 unit change in the predictor variable. The intercept is the value of the outcome variable when the slope is 0. Of these two coefficients, we are primarily interested in the slope because it tells us about the relationship between the predictor and outcome variable. Always interpret the slope when describing your regression results. The intercept is less interesting and something we rarely interpret or describe in a written report. Using these equations for our example data results in an intercept of negative 14.12 and a slope of 1.19. The figure shows this best fitting line. It has a sum of squares residuals of 49.90. There is no other line that will produce a lower sum of squared residuals for these data. Interpreting the slope, we can say that child height increases by 1.19 inches for every 1 inch increase in mid-parent height. Now that we have obtained the best fitting line that we can use to make predictions, we would like to know about the quality of the predictions. That is, we would like to know about the accuracy of the predictions that we are trying to make. The standard error of the estimate is a statistic that reflects the accuracy of the predictions. It is on the same scale as the outcome variable, and the magnitude of the standard error of the estimate depends on the scaling of the outcome variable. However, values close to 0 indicate that the observed values of the outcome are typically close to the predicted values. That is, the points will lie close to the fitted regression line. As the value increases, the typical distance between the observed values of the outcome and the predicted values increase. That is, the points move away from the fitted regression line in a vertical direction as the standard error of the estimate increases. If you look closely at the equation for the standard error of the estimate, you will see that the quantity in the numerator is the sum of squared residuals. Thus, by using the equations for the slope and intercept, you will obtain a line with the lowest standard error of the estimate. Let's go back to Galton's height data and compute the slope and intercept coefficients. The scatter plot shows the best fitting line, which has an intercept of 19.92 and a slope of 0.71. An example write-up for our correlation and regression analysis is shown here. The correlation between mid-parent height and child height was 0.5. Therefore, 25% of the variance in child height was explained by mid-parent height. The slope of the best-fitting regression line indicated that child height increased by 0.71 inches as mid-parent height increased by 1 inch. The standard error of the estimate was 2.24 inches. This paragraph summarizes our results, but there's another step that is needed. To be complete, we would need to relate these results to the underlying theory about heredity. That is, we would need to explain what these results mean for the study of heredity. This last step requires expertise in the study of heredity, and presumably Galton made this connection. However, we'll skip it here. Just keep in mind that as you're writing up your regression results, it's always important to tie them back into your underlying theory. Simple linear regression requires several assumptions. First, the outcome variable must be continuous, either interval or ratio. In most applications, the predictor variable is also continuous. However, we can use nominal or ordinal predictor variables if we recode the variable in a particular way. Recoding the predictor variable is an advanced topic that won't be discussed here. For now, use regression with a continuous outcome variable and a continuous predictor variable. The second assumption is independence. This assumption requires that responses for one participant in the study do not affect responses for another participant. For example, suppose we conducted a survey about satisfaction with the economy. If one participant copied the responses of another participant, independence would be violated. The assumption of linearity is the same as it was with correlation. We assume a linear relationship between the predictor and outcome variables. It can be checked by looking at a scatter plot or through a residual versus fitted plot. Homoscedasticity refers to the variance of residuals. If homoscedasticity is satisfied, the variance of residuals is consistent across all predicted values. We will look at some plots that will help you understand the assumption of homoscedasticity. The assumption of normality means that the outcome variable is normally distributed at each value of the predicted variable. Homoscedasticity and normality do not affect our ability to find the best fitting regression line. They are assumptions that we need to make inferences about the predictions, or inferences about the slope and intercept coefficients. Nevertheless, we will check these assumptions whenever we use regression. To check the assumptions of linearity and homoscedasticity, we use a residual versus fitted plot. In this type of plot, predictive values are on the x-axis and residual values are on the y-axis. Here you see three examples of a residual versus fitted plot. The figure on the left is an example of a plot when the assumption of both linearity and homoscedasticity are satisfied. There is a gray dashed horizontal line drawn from the y-axis at 0 in this plot. That line represents the case where the residual is 0. The red line in the plot is a nonparametric regression line. If linearity is satisfied, the red line should be very similar to the horizontal line at 0. Here we see it has a few bends, but they're small. This figure supports the assumption of linearity. To judge homoscedasticity, we look at the variability of the residual values at each level of the predicted or fitted values. The plot on the left shows that the variability of the points is similar across all levels of the x-axis. Thus, it supports the assumption of homoscedasticity. The middle plot shows the case when homoscedasticity is satisfied, but linearity is not. There is a clear and prominent curve to the red line. The points also clearly follow a curve. Thus, the middle figure shows the case when linearity is violated. The figure on the right illustrates a linear relationship that lacks homoscedasticity. The vertical distance between points is small when the predicted value is below -2. That pattern contrasts with the range of points when the predicted value of y is above 1. The points appear to form an arrowhead in the plot, which signals heteroscedasticity. To see homoscedasticity and heteroscedasticity more clearly, I have added blue lines to the plots. On the left, notice that the spread of points between the blue horizontal lines is fairly even across levels of the predictive values. This shows homoscedasticity. In the figure on the right, the blue lines are no longer horizontal. They form an arrow pointing to the left. This pattern shows heteroscedasticity. These figures show examples of using residual versus fitted plots to check the assumptions of linearity and homoscedasticity. However, they are not the only possible examples. They are not exhaustive. There are other ways that the data may be nonlinear or heteroscedastic. To check normality, we use a normal QQ plot of standardized residuals. A standardized residual is a residual value divided by the standard deviation of residuals. A QQ plot shows the empirical percentiles on the y-axis and the theoretical percentiles from a standard normal distribution on the x-axis. The assumption of normality is supported when the points in this plot fall along a line drawn at a 45-degree angle, because it means that the empirical percentiles for the standardized residuals are similar to or the same as the theoretical values from a normal distribution. The more that the points deviate from the line, the less support for the assumption of normality. The figure on the right is a normal QQ plot, and it shows support for the assumption of normality. These two plots show an example of when normality is not supported. The histogram on the left indicates that the standardized residuals are positively skewed. When we create a normal QQ plot, the points clearly deviate from a straight line drawn at 45 degrees. Note that larger than expected values appear above the line, and smaller than expected values appear below the line. In this example, skewness results in percentiles that are larger than expected at the extremes, and percentiles that are smaller than expected in the middle part of the distribution. You should always check the assumptions of a statistical procedure. If you fail to support an assumption, you should consider using an alternative statistic that does not require the assumption. At a minimum, you could continue to use the method but inform the audience that an assumption has been violated. That way, the audience can decide whether to trust your results or not. The approach you should never follow is trying to hide violated assumptions. There are limitations to the predictions you can make with your results. It is okay to use a value of the predictor variable x that was not observed in your data, but it is within the range of the observed values of the predictor variable. Interpolation is acceptable, but extrapolation is not. Extrapolation occurs when you make a prediction for a value of the predictor variable x that is outside the range of observed values. In terms of the Galton height example, we can predict child height when midparent height is 73.2. This particular value of midparent height was never observed, but it is within the range of values we observe for midparent height. As an example of extrapolation, we should not try to predict child height when midparent height is 85 because we never observe such a large value of midparent height. Keep this limitation in mind when making predictions. When you compute a correlation, it does not matter which variable is the independent variable and which one is the dependent variable. It does matter when you do regression. Be very careful about the way you conduct your regression. The figure on the left shows an example of using x to predict y, and the figure on the right shows an example of using y to predict x. Notice that the regression line is different. In order to conduct the regression the correct way, pay close attention to the language. You may be asked to use x to predict y, which is shown in the figure on the left. This regression could also be stated as an analysis that regresses y on x, or as the regression of y on x. These phrases all mean the same thing. X is the predictor variable, and y is the outcome variable. Be aware of the terminology because statistical software expects the input to be in a particular order. In the statistical software R, the linear models function is what we use to conduct regression. An example of using the linear models function is shown below each plot. In order to use x to predict y, use the call shown on the left. It is a different call than the one for using y to predict x. Which one should you use? Use the example on the left. In standardized regression, we first transform the original values to z-scores and then conduct the regression on the z-scores. With this transformation, the resulting intercept will be 0 and the slope will be the correlation between the two variables. The slope is interpreted in terms of standard deviation units. That is, the slope tells us the amount of change in the outcome variable in standard deviation units that occurs when the predictor changes by 1 standard deviation. Standardized regression is typically used in multiple regression where you have multiple predictor variables. By standardizing the variables, the regression coefficients are comparable, and one may compare the strength of each predictor variable. You may hear people use different terms when discussing regression. It's important to know which ones are synonyms. The outcome variable is also referred to as the dependent variable, the response variable, the regressand, or the left-hand variable. It is the left-hand variable because it appears on the left side of the regression equation. In a scatter plot, we put the outcome variable on the y-axis. The predictor variable is also referred to as the explanatory variable, the regressor, or the right-hand variable. It is the right-hand variable because it appears on the right-hand side of the regression equation. We typically put the predictor variable on the y-axis of a plot. In summary, simple linear regression is a statistical procedure that allows us to use one variable to make predictions about another. It amounts to fitting a straight line to a scatter plot. In using regression, we must always evaluate the quality of the predictions and check the underlying assumptions. We typically use correlation and regression together. Therefore, always interpret the correlation, the coefficient of determination, and the slope coefficient when reporting your results.